There's some different types of categories of DC motors available. We've got permanent magnet motors. Those are typically simple motors, little hobby motors, smaller toy motors and things like that will have permanent magnets in them. They're mainly used for low torque applications because the magnetic fields that we can create with those permanent magnets are not as strong as we can create using other techniques, using those field windings that I talked about in a previous video. The other types are series wound. In that type, the field winding is wound in series with the rotor winding. That means there's only one pathway for the current to spin around that motor, and that'll have an advantage to it that we'll talk about. We've got shunt wound windings. This is the field winding, mind you, the magnetic field that's being created in the stator. So the shunt wound is wound in parallel with the winding of the rotor. That also has advantages that we're going to talk about. And then we've got compound wound, and that one is both. It has a winding that is in parallel and a winding that is in series with the windings of the rotor. And that tries to split the difference between the advantages of the two, of series wound and shunt wound rotors. Since we already saw the permanent magnet motor with the simple example in the previous video, I'm just going to skip right on to series wound motors here. This is an example of a series wound diagram. You can see that one field winding creating the south pole is in series with the field winding creating the north pole, which is in series with the winding that creates the field in the rotor itself. And there's only one direction that the current can flow through this system. They all have to march in a line with each other. Now, one of the biggest advantages to this design is that it doesn't matter if it's DC or AC. It doesn't care if the electrons are marching around in this direction or if they're marching around in the other direction. So this is actually a universal motor. It'll run on both DC and AC current. Shunt wound is next up on the list. Shunt wound is when we have our field winding in parallel with the winding of the armature. It creates a very high resistance in the field winding and only allows a small amount of current to move through there. That means that most of the current actually goes through the armature. The rotating part is what gets all of the current. And the advantage to that is that when you load the motor down, it only has a slight effect on the motor's speed. The other advantage is that the field current can be controlled by putting a variable resistor in line with that. And when you control the field current, you control the strength of that field, and that changes the speed of the motor. So you can speed the motor up or slow the motor down depending on how much current you allow into that field winding. And here's a diagram of a shunt wound motor. As you can see, it's the field windings are in parallel with the winding for the rotor. Here's a separate schematic diagram of that same system. And if I were to place a variable resistor right here, I could control how much of the DC current was allowed through this field winding, which modifies the strength of this field, which modifies how much torque is produced as this thing is spinning, and changes the speed that it'll spin at. A compound wound DC motor combines the two, a series and a shunt wound, to create a series parallel situation, and that gives us high torque and good speed regulation. And here's a diagram of that, where it has one field winding that's in series, and it has one field winding that's in parallel, so that we can put our resistor here to control the speed with this field and still have good current flowing through this one to generate that torque that we want.